Okay, year 12, this is lesson 2 of the group 2 topic, and it's actually lesson 2 of 2. This takes us to the end of what is a very short chapter. Back in lesson 1, we considered a lot of things that you're already familiar with. Things like trends down the group, like atomic radius and ionization energy. Also looked at the reactivity as you go down the group, and perhaps related that to your knowledge of group 1 and applied it. Now today we are going to look at a lot of things that are still familiar to you, but we're going to add in significant new chemistry as well. It's really important that when you get to a task, you pause the video and you try it for yourself. And if you don't know the answer and you can't reason it out, look it up, because you finding it and making the effort to actually get that information is going to help you to deepen and embed that learning far more than simply watching the video and noting down the answers when I get to them. So with that in mind, let's get to the first couple of tasks, working through the booklet. And we have got 2 questions here. We've got magnesium reacting with water to make magnesium hydroxide. A lot of information there, not all of the information you need to do the equation. It tells you it's a slow reaction. So you've got 2 tasks to do when you pause this video. 1, I want you to write the equation out, including state symbols. And 2, I want you to explain why the reaction would be faster if carried out with steam rather than water. So we'll take a look at the answers. To begin with, the equation. We've got magnesium and we've got H2O. We were told that they were the reactants. We were also told that one of the products is magnesium hydroxide. Now, to get the formula for magnesium hydroxide, you have got to know magnesium is in group 2, so it loses 2 electrons to form an ion, so its charge is +2. You also need to know that a hydroxide ion has a charge of -1. You simply have to learn it. But looking at what you've done with redox and working out oxidation states, if you remember the rules that oxygen has an oxidation state of -2 and hydrogen +1, that helps you to get to OH being -1. So we've got our magnesium hydroxide, but it's not the only product. And this is where perhaps you need to look to your knowledge of group 1 and apply it to this and adapt it. Because in the group 1 metals, when they react with water, we make hydroxides, but we also make a gas. It's a gas that will explode with a squeaky pop if I insert a lit spill. And it's exactly the same here. We're going to make hydrogen. And we have got to remember that hydrogen is a diatomic molecule. It exists as H2 molecules. If you miss that key fact, it makes the balancing wrong. It makes the equation incorrect. Now from there, we've still got further to go. We need to balance it. And at the moment, I can look on here and see that I've got 1 magnesium on either side. But if I take oxygen as an example, I've got 2 on the right-hand side. I've only got 1 on the left. So I'm going to add a 2 to balance that one. Now, you'll also notice that that puts me with 4 hydrogens on the left, and I've got 4 hydrogens on the right. So it is fully balanced. Moving on, we've still not finished the equation, because I did say at the start to include state symbols. Now, magnesium is a solid, fairly straightforward. Water is always going to be a liquid rather than aqueous. Obviously, it can be solid or gas as well with ice and steam, but you will never have aqueous water. And that's because aqueous means dissolved in water, which is not the case here. Now, it's also fairly obvious, I hope, that hydrogen is a gas. Magnesium hydroxide as an ionic compound that is in solution will be aqueous. So we then move on and look at why the reaction would be faster if carried out with steam. And this again is going back to your knowledge of kinetic theory, of collision theory. If you go to steam, that's a higher temperature, and that tells us more kinetic energy. And if there's more kinetic energy, that means that more particles have energy equal to or greater than the activation energy. So the wording of this is really quite important. You have got to be quite clear with it. And even more so in the final section, because we also need to say that that leads to a greater frequency of successful collisions. It's not really right to say there are more successful collisions. It's got to be about the number of them within a given time. The fact that it is far more likely that a collision will result in a reaction. Okay, we're going to move on to the next task. This is an experiment that you will almost certainly have seen at GCSE. If you're not familiar with it, if you can't remember it, you can either work through, try and answer the questions as to what you think you would see, or you can look on YouTube alongside this, open up a new tab and search magnesium with steam, and you'll find lots of videos where people have done this and you can watch the observations. But I want you to describe what you would see in this reaction. There's a lot of it given away within the diagram itself. Not a scientific diagram, I should point out. Please never draw things like this. And there's also an equation. And it's interesting that I'm asking for an equation for magnesium once again with H2O. That implies there is a difference. So we'll see if you can remember what that is from GCSE. So now you've had a go, let's take a look at the answers. Now, once again, we can start the equation off quite simply. We know that we're reacting magnesium with water. The significant difference here is that we don't make magnesium hydroxide. Now, there is no water to dissolve in to get to the hydroxide, and it's for that reason that the reaction stops at magnesium oxide, but we still make the H2. And we can prove that by igniting the gas that comes out of the delivery tube, as we can see on the diagram. So there's one of the observations actually, and I'll talk more about those in a second. Now, finally, I need to check balancing and I need to check state symbols. I've got one magnesium, I've got two hydrogens, I've got one oxygen, it's balanced. So all I need to do is add the state symbols. Magnesium is solid. You'll notice here an error. Can you spot it? The water should not be liquid. And the water should not be liquid because we're reacting with steam. So, making that correction, this is a really common error that you want to try to avoid. Okay, moving on, we've got the magnesium oxide as a solid and the H2 is a gas. So then we get to the observations. Now, even if you don't remember this reaction, I'm hoping that you remember other reactions of magnesium that helped you to do these observations. First of all, we've got the flame where we've ignited the H2. As I say, the diagram tells us that. But we've also got a white ash as the magnesium is formed. Now, magnesium oxide is often what you make when you do experiments on conservation of mass at GCSE. There is one other observation as well, and it'd be interesting to see if you remembered the very specific observation when you burn magnesium. And what we have is a bright white flame formed. So it's that experiment that you might remember you had to watch through a filter or you weren't allowed to look at directly because it's so bright it can actually damage the retina. So we've got the key observations and it would be reasonable to expect that you're going to be asked those in the exam. Okay, moving on to the next task. We've now got other reactions in group 2 with water. So we've done magnesium with cold water. How are we going to adapt what we know from there to calcium, strontium and barium? Have a go at the equations and when you're ready, move on with the video. Okay, so to answer this, I'm going to go through slightly differently. I'm going to start with my metals. They are all solid. And the reason I'm doing it this way is I'm hoping you can see the pattern very clearly. I'm hoping you've already spotted it. Now, when I react them, I'm reacting them with water. And water, in this case, is a liquid because it's cold water. Obviously, we have the arrow goes on to B, and we're making the hydroxide. Now, we spoke at length earlier about magnesium hydroxide being MgOH2, and that's because OH is -1 and Mg is +2. All group 2 metals form ions with a +2 charge, so they will all follow the same formula. They will all be MOH2, where the M is the group 2 metal. They're all ionic, there's water present, so they are all aqueous. And finally, we add the H2, and the H2 is a gas. So we've got the equation, we've got all of the component parts. Finally, we need to balance it. Well, you've balanced the magnesium hydroxide one already, and you'll see it's exactly the same as we go through here, 2H2O. And in every single one of those now, you have a perfectly balanced equation. All reasonable questions for an examiner to give you within an A-level exam. Okay, moving on to the next task, and we've got two properties that you're going to have to know in really quite significant detail, and that's the solubility of group 2 sulfates and group 2 hydroxides. So we've already looked at the hydroxides being made actually. We've not said so much about the sulfates yet. But there's information on this page that I want you to read really carefully so that you can then answer the question at the bottom. So pause, read, have a go, and when you're ready, move on. Okay. So we've got in the blue box here, barium +2 ions are incredibly toxic to humans. If they enter the bloodstream in aqueous form, they are fatal even in small doses. That's fact number one. Barium ions are dangerous. So then we have fact number two. Barium sulfate is what's commonly known as the barium meal. Now, the barium meal is something that if you're having an X-ray potentially of the gut, of the intestines, you drink it and it will absorb X-rays. So what you get is a far more pronounced X-ray, and you get to see any irregularities, anything that might need investigating further. So to do that, you've got to drink the barium meal, and that's barium sulfate. So we've got two contradicting pieces of information. Barium ions are incredibly toxic. People drink barium sulfate sometimes before an X-ray with no ill effect. So what conclusion do we draw? Well, it's all down to the solubility. And barium sulfate is incredibly insoluble. It's totally insoluble. So it doesn't break down into its ions. It doesn't break down and move into the bloodstream and move into the fluids within your body. And that's why the barium ions can't have their toxic effect. Now, if you then look at where barium is on the periodic table, it's down at the bottom of group 2. So what we've got here is a really practical application that tells us barium sulfate is insoluble. It's at the bottom of the table. So solubility of sulfates, of group 2 sulfates, decreases as you go down the group. You need to know that trend, and you need to know about the barium meal, and you need to know about the toxicity of the barium ions. Everything spoken about on this page is absolutely vital. We're going to move on. And we're going to look at a practical. Now, obviously, we can't do the practical now, so I am going to ask you to look this up, pause the video, do a bit of research and see what you can find. You could probably have a go at the ionic equation for yourself, if you remember those from GCSE. But don't just wait for the answer. I keep saying it, but you'll get far more from it if you do this for yourself first. So have a go. And now we're ready, let's move on. The test is actually relying on the fact that barium sulfate is insoluble. And we know that if something is insoluble, it doesn't dissolve in water, so it will precipitate out. We will form a solid. We're putting two liquids together here. And if there are sulfate ions present, when I add the barium chloride, I will end up with a white precipitate. So you need to know the method and you need to know the positive test for sulfate ions. The ionic equation. Now, in an ionic equation, you will break down anything that's ionic and aqueous, but you won't break things down that are ionic and solid. So let's take a look at the ions in these different components. I've added barium chloride to, in this case, I've added sodium sulfate with my sulfate ions present. My barium chloride is ionic, so I break it, and it's aqueous, so I break it down into its ions. My sodium sulfate is ionic and aqueous, so I break it down to its ions. And my sodium chloride is ionic and aqueous, so we break it down to its ions. But barium sulfate is a solid, it's insoluble in water, so we don't break it down to its ions. Now the next step here is to remove spectators. Spectators have no part to play in an ionic equation. And I can see here that I have got chloride ions, 2Cl- on both sides. If it's not changed, don't leave it in there. I've also got 2 sodium ions, so I can remove them. And finally, I'm going to write out the equation as it exists in full, and you can see that the overall equation for the ionic equation for this reaction, B82 plus SO42 minus, goes on to be BaSO4. We're going to finish off this lesson by looking at trends in solubility of hydroxides. Again, I want you to read through this, pause it, answer the questions, and then we will review. So now you've had a go, we will take a look at the first one. Magnesium hydroxide is used to treat indigestion. You have milk of magnesia, it will neutralise stomach acid, whereas barium hydroxide would actually be far too dangerous to use. Now that hopefully is enough information to tell you that solubility increases as you descend group 2. And to reinforce the idea, why would we not use a stronger alkali? Why would we not use an alkali that dissociates far more, dissolves far more? Well, barium hydroxide, for one thing, would be barium ions, which we've already established are toxic. But even strontium hydroxide, it would be far too alkaline. So if it got to your stomach acid, it would neutralise it, but it would actually be so corrosive it would burn away your throat lining on the way down. So for that reason, we don't do it. They would be corrosive. And to finish off, barium hydroxide fully ionises in solution. So we are looking here at breaking the barium hydroxide down into its ions. So I take my barium hydroxide, it's AQ, I break it down to my Ba plus 2, it's group 2, so we know it's plus 2, my 2 OH minuses, and we have the equation. That takes us to the end of group 2. You have absolutely everything content-wise that you will need. We're going to do some questions to build on that, on the whole of the topic, and they're going to come through on forms that I would like you to submit by Monday's lesson, and I will get them marked for next Friday. But I do think it's worth going back through and reviewing this content more than once to make sure that you're happy with it. So this video is available for you to go back and review as and when you're ready. Thank you very much for listening. Any questions, get in contact with me. Thank you very much. Bye.